Welcome to this lecture. As before, let us first recall what we have discussed so far, and then we shall start with the topics of this lecture. So, in this week, we have started talking about events coming from certain random experiments, and when you look at the collection of all events in connection with a random experiment, we end up with certain structures on these collections of events. Remember that these events are special subsets of the sample space, where sample space means the set of all outcomes. Now, once you have that collection of all events, we considered the structures of sigma fields and fields on top of it. We studied general definitions of sigma fields and fields corresponding to any non-empty set. We looked at many of the examples of these. We had shown that all sigma fields are fields but not the converse. So we have shown an example of a field which is not a sigma field. For examples of fields, we have done two different types of approaches. One was a bottom-up approach, starting from the trivial sigma field and adding sets to it and obtaining examples. Another was a top-down approach, starting with the power set sigma field and removing certain sets in a certain way so that I get a sigma field. In the second way, we had constructed what we call as sigma field generated by certain collection of sets. And in this regard, in this way, we have obtained a very important object or very important sigma field on the real line, which we called as the Borel sigma field. This was defined as the sigma field generated by the open sets in the real line. After that, we have discussed that there are other classes of sets which also generate the same sigma field, the Borel sigma field on R. For example, all closed sets will also generate the same things. We have looked at open intervals, left open, right closed intervals, and so on. And all we have seen is that if we look at classes of such sets, then they generate the same sigma field, the Borel sigma field. So Borel sigma field has a very nice collection of events or very nice collections of subsets of the real line. We have also remarked that there are subsets of the real line which are not Borel sets, meaning not in the Borel sigma field. We shall see examples of those later on. And one other thing we have discussed in the last lecture, in fact, is that there are notions of Borel sigma fields on extended real lines and also for higher dimensional Euclidean spaces and also on Borel subsets of the real line. So we have discussed all these concepts. Okay. Now with that at hand, we now start with the today's lecture. We are now moving on to the slides. So this is involving limits of sequences of subsets. So I am given some non-empty set, call it omega, and I am interested in sequences of subsets, so a1, a2, an, and so on. Now the idea is this: involving the sigma fields, we have been able to work with countable unions and countable intersections, and these in some sense are certain kind of limiting operations, and that's what we want to highlight and do much more closer analysis in this lecture. So we start off with some ideas of sequences of sets, and we introduce some certain notions of monotonicity involving sets, so that we can call that a certain sequence may be increasing or a certain sequence may be decreasing. So let's start with the definitions. So I say that I am given such a sequence of sets a1, a2, an. If it so happens that a1 is contained in a2, a2 is contained in a3, and so on. So an will be contained in an plus 1. So then we will say that the sequence an is non-decreasing or increasing. Okay. In this case, what happens is that if you look at the countable union of these sets, that's what I call as capital A, let's say, then we shall say that an is increasing to A. Alright. So you have these sets A1, then it increases to A2, then it increases to A3. So you look at all these unions of all these sets. As they increase, you are getting bigger and bigger sets, and at the end, if you denote that set as capital A, then we say that the sequence AN is increasing to A. Now in this regard, we shall use this notation AN upper arrow or up arrow to denote that the sequence is increasing or non-decreasing. Okay, so here the notion of monotonicity is simply involving set inclusions. So AN should be included in AN plus 1, and this should happen for all n. Great. Now I am looking at this notation that if A is the complete union of all these sets AN, I will write AN increases to A. So this up arrow to A. So that's what the notation means. We shall see examples of this. But conversely, you expect to have a notion in the other way. So if it so happens that E1 is the largest set, then you get A2. So that's slightly smaller. So A2 is contained in A1. Then A3 is contained in A2 and so on. So AN will contain AN plus 1. If it happens for all such n, then we say that the sequence AN is non-increasing or decreasing. Alright. So in this case, we are using this notation as expected, AN down arrow. So this will mean that the sequence of sets decreases. Now once you look at this sequence of sets, you expect that you first start with A1, then you go to a smaller set. So you can think of A2 as the intersection between A1 and A2. Then when you look at A3, you can think of it as a intersection between A1, A2 and A3. So in this way, you can expect to get the limit to be this complete intersection of all these sets. And let's say you denote this complete intersection by capital A. Okay. Then we are going to say that this sequence AN is decreasing to capital A. So provided the sequence is decreasing, look at this complete intersection and write that AN decreases to A or AN down arrow A. So this simply means that these sets will decrease and are going to decrease to the complete intersection, this complete countable intersection. Alright. So we have these two notions that we have introduced, and what you require is that first of all, for increasing sequence, you require AN to be contained in AN plus 1 for all n, and for decreasing sequences, you require AN to contain AN plus 1. So you have a decreasing sequence of sets in the second case. Alright. So now you first make a connection with these two notions. So you can immediately try to check that it actually shows that if AN is a increasing sequence of sets and increases to A, then it will happen if and only if their complements are decreasing and it actually decreases to the set A complement. So try to check this. Okay. So this is a if and only if condition that connects the notion of increasingness to the decreasingness of another sequence. So just to understand this notion better, let's look at certain examples. So take this sequence of intervals AN on the real line. So AN is minus n to plus n. So for n 1, 2, 3, all the non-negative integers, all positive integers. Then what happens? If you look at AN plus 1, that starts from minus of n plus 1 to n plus 1, right? So therefore AN plus 1 is a bigger set and it will contain AN. So since AN is contained in AN plus 1 and this is true for all possible small n, then AN is increasing. Now you are interested in what happens to the limit. So the sense of limit here is simply for the increasing sequence of sets, all we have discussed is the complete union. So what is the complete union of all these ANs is that the whole real line. So what you expect is that you look at all these intervals minus n to plus n, take the union as n goes from 1 to infinity, it will cover the whole real line. So the complete union is the whole real line. So that's the first example that you keep in mind. Now here is a very interesting example. So again we are restricting our attention to the real line. So fix a point x, a real number, and then look at this type of sets an. So this is again minus infinity to the closed, so this is a closed interval minus infinity to x minus 1 over n. Okay, so therefore these sets will look like something like this. So minus infinity to x minus 1, so that corresponds to n equal to 1. Then for n equals to 2, you get the set minus infinity to x minus half, and so on. Now we can easily check that these sets an are increasing, and now you are interested in what is the complete union, and it so happens that if you try to verify this complete union, you can rewrite it in this notation that it actually, the complete union is actually this open interval minus infinity to open x. Okay, so it will not contain the point small x, but it will be the open interval minus infinity to open x. So that's a very interesting observation, that you have these collections of closed intervals, but their countable union is giving you an open interval. So please check this. And similar fashion, there is this interesting example. So here I am now, instead I am again fixing x, but I am looking at different types of closed intervals. So I am taking minus infinity to x plus 1 over n closed. So again, for n equal to 1, you will get minus infinity to x plus 1. Then for n equals to 2, you will get minus infinity to x plus half, and so on. Now you can again check that ans are decreasing. And what is the limit? So the limit here, notion of limit is simply the complete intersection. So if you now try to check that what is the complete intersection here, you will end up with a closed interval. So intersection of all these closed intervals will give you this closed interval minus infinity to closed x. So again, try to check this. So this is a very interesting notion of convergence for the sets. So you have certain limits of sequences here when sets are increasing in a certain way or decreasing in a certain way. So using these notions, we now introduce an interesting type of collections of sets. So I look at a collection of subsets of omega, some non-empty set, and let's call this collection script f. So this is some arbitrary collection so far, but I ask that there are certain properties. So I will call this collection as a monotone class if it is closed under countable increasing union and countable decreasing intersections. What do I mean by this? Again, so let's go to the exact descriptions of the operations countable increasing unions and countable decreasing intersections. Okay, so the first property means that you take an increasing sequence of sets and look at their countable union. So as described earlier, if you are looking at an increasing sequence of sets, you are going to look at the complete union, the complete countable union. And since these sets are increasing, you can call this complete union as a countable increasing union. Okay, so that's what I mean. So what we want is that if you have an increasing sequence of sets in this collection script f, I want their complete union to also belongs to the collection script f. So that's the first property, and this is what we will call as closure under countable increasing union. And once you have that property, you again will expect that the similar property for the intersections. So if you have a decreasing sequence of sets in the collection script f, and if it so happens that ans will decrease, and therefore they are going to decrease to the complete intersection, right? Now if ans are decreasing, then the complete intersection you can now visualize as the countable decreasing intersection. So that's what I call here, and therefore that's what your set capital A is. And here what you want is that if an is a decreasing sequence of sets and coming from this collection script f, I want that complete countable intersection, the countable decreasing intersections, to belongs to that collection once more. So this I will call as closure under countable decreasing intersections. So once you have a collection of subsets script f with these properties, that it's closed under countable increasing unions and countable decreasing intersections, I shall call it a monotone class. So now all these operations that you expect, I want to see examples of this. So the first examples that you will immediately get are sigma fields. So no matter what kind of sets you take, as long as they are increasing and looking at countable unions of those. So countable unions are allowed in sigma fields. So therefore these sigma fields will satisfy closure under countable increasing unions. So remember, sigma fields will support countable unions. So in particular it will support countable increasing unions. So therefore it's closed under countable increasing unions. Similarly, for a sigma field you have closure under countable intersections. So in particular it will also support closure under countable decreasing intersections. So therefore all sigma fields are monotone classes. We are not going to look at many general classes of monotone classes, many explicit other examples. We will restrict our attention to sigma fields, but it's a good exercise to find an example of a monotone class which is not a sigma field. Try to work this out. There are many examples, you can work them out. So we are not going to use too much of monotone classes in this course. We are not going to spend too much time on it, but it's always good to have an understanding of monotone classes, and that's why this exercise will help you. So please try to find examples of monotone classes which are not sigma fields. In fact, this monotone classes and sigma fields and fields, they have very interesting connections in between them. So just to describe that, here are now a set of exercises for you. So exercise 12 here, this is in relation to a field, and that's for something we are going to use later on. Let's take some number of sets, finite number of sets in a field. So a1, a2, an are sets in a field. Consider these sets, let's say b1, b2, bn and c1, c2, cn. I define them. So what are these b1, b2, bn's? So I define b1 to be a1 itself, but I look at bi for I equals to 2 onwards, for next numbers onwards, to be ai, but I remove all the items, all the elements that I have seen so far. So by that I mean that I look at the unions of the edges from 1 to I minus 1, which we have already encountered so far, and then I take them out from ai. Okay, so I look at a1 for b1, then b2 is simply a2 intersection with a1 complement, then b3 will be a3 intersection with a1 union a2 whole complement. So like that. So we are looking at the new terms that are arriving in ai, but I don't want the terms that I have already seen up to ai minus 1. So those are I am removing. So that's how I am defining bi's. And what are ci's? Ci's are nothing but the unions from 1 to I of the sets aj. So c1 is a1 itself, but c2 is a1 union a2. So what you can now try to show is that if the sets a1, a2, an are in the field, then the sets b1, b2, bn are also in the field. But using the structures of the bi's as defined here, you can try to show that bi and bj are pairwise disjoint. By that I mean that if I not equals to j, then bi and bj will not have any common element. So their intersection is an empty set. Similarly, for the ci's, which are defined as some kind of a cumulative union, so what you are having is that for if a1 into an are in the field, then c1, c2, cn are also in the field. Interestingly, you can also show some certain connections with ci's and the sets bj's. So you can again show that ci's are nothing but again kind of a cumulative union of the bj's. So try to verify these relations. And then here is the interesting connection, that if you can have a collection of subsets which is a field as well as a monotone class. So remember, fields will allow you complementation, finite unions and finite intersections. A monotone class allows you countable increasing unions and countable decreasing intersections. So suppose a collection of subsets allow all these operations for you, then try to show that script f must be a sigma field. So field together with a monotone class implies you actually get a sigma field. And a hint for this is use this previous exercise that we have just discussed. And an important theorem or an important result follows these ideas, and this is what is called the monotone class theorem. So let's come to this point. So let script f be a field and script m be a monotone class with the property that the field is contained in a monotone class. So I am looking at a non-empty set omega. I am looking at some collection of subsets which is script f with these complementation, finite unions and intersections, that is a field. And then I am looking at a monotone class script m, again on the same non-empty set. So on monotone class I have countable increasing unions and countable decreasing intersections with the property that the original list of field, original collection of sets script f, that is a field, all those sets are already included in the list in the collection script f. So that's what this inclusion means, as we have discussed earlier. Now the conclusion of the theorem says that under this situation the sigma field generated by the collection by the field is contained in the monotone class. So this is a very important result that connects fields, the generated sigma field and the monotone class. So again, just to repeat, if you have a field that is contained in a monotone class, then the sigma field generated by the field is also contained in the monotone class. So all we are saying is that if you have a field, then you will also expect to have sequences of sets from the field, and then their complete unions and things like that also will belongs to the monotone class. That's what this generated sigma field contained in monotone class implies. Okay, so if you have a field contained in a monotone class, then the sigma field generated by the field is also contained in the same monotone class. So this is a very important theorem, and we do not prove this, we are just stating it as part of the course. Now what are the implications of this? So the way we are going to use this is discussed in this note. So if you have two collections of subsets, arbitrary collections of subsets, script C and script D. So again I am fixing the non-empty set and discussing this. So here, if it so happens that script C is contained in script D, so this is a larger connection, script D is a larger collection, we sometimes shall need to prove that the sigma field generated by script C is contained in script D. We shall need that. We will discuss such situations later on. And then to claim such inclusions, provided that we have script C is already there inside script D, we shall need certain results. And based on our discussion so far, we have the following conditions which imply this. So again, the setup is that we are already given the information script C is contained in script D, but I want to claim that sigma field generated by script C is also contained in script D. So what are the situations? So the first situation is this, that if script C is contained in script D and D is a sigma field, then since sigma field generated by script C is the smallest sigma field containing script C, as a definition, immediately it will follow that sigma field generated by script C is contained inside script D. So this is something we discussed as part of the previous lecture. But then there is another condition which we just got introduced to in the monotone class theorem, and that suggests that if you have a field and if D is a monotone class, then the same inclusion holds. So that means if C is a field contained in a monotone class script D, then the sigma field generated by the field script C is also contained in script D. So this is the implication provided in the monotone class theorem. We shall see applications of this observation later on, and this result is again related to the principle of good sets. We had mentioned this earlier in note 22, but again just to repeat, due to time constraints we are not going to discuss these things in detail later on. Now we come to a very interesting operation called limit superior and limit inferior of sets. So again, just to recall, so far what we have done is that we have looked at increasing sequences of sets and decreasing sequences of sets, and we have discussed certain ideas of limits there. So in case of increasing sequence of such sets, we had looked at the complete union, the complete countable union as the kind of a limit, and for the decreasing sequences of sets we had looked at the complete intersection as the limit. Now it may so happen that you have a general sequence of sets which is neither increasing nor decreasing. In that case you may ask, okay, is there any notion of a limit? Again we take motivation from real analysis. So in real analysis, if you are given a general sequence of real numbers, it need not be convergent, it need not have a limit. However, you have these notions of limit superior and limit inferior, and they always exist for a real number sequence. Of course, limit superior and limit inferior for a sequence of real numbers can be plus minus infinity, but they always exist. So we take motivation from that and define the limit superior and limit inferior of a sequence of sets. How do you do this? So I am given this sequence of sets a1 to a and so on. I define this limit superior this way. So I first look at unions from n onwards. So that's the inner union. The outer intersection says that I now look at intersections of such things. And limit inferior is exactly the opposite thing. I first look at intersections from n onwards. That's the inner operation. And outside I am now looking at unions of all such things. So get used to these notations, limit superior of sets an and limit inferior of the sequence ans. Okay. So I have a sequence of sets an and I am defining limit superior and limit inferior this way. Now you shall ask, what happens as examples? Now just for your hands-on examples, I have left you some exercises. So consider these three types of sequences, an, bn and cn. So an is the sets 0 to n closed. As you can immediately see, these sets an increase. What about bn's? They have some kind of a oscillating feature. You see, if n is odd, like n equal to 1, 3, 5, 7, so on. So I am taking the sets 0, 1, open interval. If n is even, like 2, 4, 6, so on. So then I am taking the set 0, 2. Then try to see what happens to limit superior and limit inferior. So again, the way of computations, just to give you some ideas. So just going back to computations involving limit superior, first fix some n small n. Look at this inner union first. Compute that. Try to write it in terms of one set, but it will depend on n. And then take the complete intersection as n goes from 1 to infinity. To compute limit inferiors, what you have to do? You have to do exactly similar thing. First compute the inner intersection from n onwards. So whatever you get, you write it in terms of one set, and then you take the complete union from as n goes from 1 to infinity. Try to work this out. So that is for the ans and bns, and c for the cns. So in bns, I have taken sets 0, 1 and 0, 2. These two sets, they have certain intersections. In cn, they have no intersections, but they have this oscillating type of a feature. So try to work this out. I have left them as exercises, and this will help you understand what exactly happens in terms of limit superior and limit inferior. Now there are certain interesting interpretations for limit superior and limit inferior. So if a point belongs to limit superior, so this means if you go to the definition, let's go to the definition once more. So let's look at x belongs to limit superior. So that means x belongs to this intersection, right? Intersection is outside. So that means x belongs to this inner union for all possible n. So just to repeat, if x belongs to this limit superior, that means from the definition of intersections, x must belong to the inner unions for each fixed small n, right? So that's what we write. So if x is in limit suprema of ans, then x must belong to this inner unions n to infinity for each n. But this will happen if and only if x belongs to an for infinitely many n. You try to now go back to the definition of x belonging to this union. So if it happens for each n, then x must fall in ans for infinitely such things. I am not saying that it will belongs to each and every n, but I am saying there will be some sequences of n's such that you will get x belongs to an, right? This is simply following the definition. And for this reason, we may describe the situation x belongs to the limit superior as x belongs to an infinitely often, right? So x belongs to an for infinitely many n, and in English language we shall refer to it as x belongs to an infinitely often. There is a similar interpretation for limit inferior of ans. So that is goes like this. So x belongs to limit inferior. So remember, just going back to the definition, if you look at the definition, x belongs to this limit inferior means x belongs to the union in from 1 to infinity. That means x belongs to this inner intersection for at least one n, right? So let's write that down. So x belongs to limit inferior, that means x belongs to this intersection for at least one n. So let's say that n is n naught, some positive integer, but then that means that x belongs to this intersection for all n after n including n naught, right? So x belongs to this intersection from n naught onwards. So that means x is a common element in all these AKs as k varies from n naught onwards. Okay. So for this reason, we may describe this situation that x belongs to limit inferior of ans as x belongs to an eventually. That means there exists a stage in n naught such that after that stage x always belongs to the ans. Okay, so that gives you some very nice interpretations of limit superior and limit inferior. Now there are some interesting properties that connects limit inferior and limit superior. They are given in this proposition. Again, these are some of the operations using the usual set operations, and you can easily check them. So if you look at limit inferior and look at the whole complement, that can be written as the limit superior of the complement of the sets. So that's the first property. The second property says if you look at limit superior and look at the complement, that can be written as the limit inferior of the complements of the sets. So again, these properties are simply involving the complementation, intersections and unions. So using standard set operations properties. Now in the real line, when you define limit inferior and limit superior of a sequence of real numbers, you had this property that limit inferior was less or equals to limit superior. For sets, that notion simply becomes a notion of subset. That means we are getting this property that limit inferior an is a subset of limit superior. Again, from the discussion that we have done for limit superior and limit inferior, you can immediately check this. So check that a point is in limit inferior. That means you can immediately show that it actually belongs to limit superior also. Therefore, limit inferior is a subset of limit superior. And then it will now connect to the notions of limits that we have already considered for increasing sequences of sets and decreasing sequences of sets. So if it so happens that ans increase to a, so in case of a increasing sequence, or ans decrease to a, that for the case of decreasing sequence of sets, then you can immediately check that both the notions limit superior and limit inferior exist. Of course, as per the definition here, they will match. So that's the important point here. So limit superior will equal limit inferior in the case the sequences increase or decrease, and it will actually give you the set A. So no matter if you are taking increasing sequences of sets, then A will become the complete union. So then limit superior and limit inferior both will be the complete union. If ans are decreasing, then it decreases to the complete intersection, and therefore limit superior and limit inferior will match and will be the complete intersection. So try to work this out. So that is left as exercise. These are very simple exercises involving set operations. Now again, some further comments. If it happens for some sequence an that limit superior and limit inferior match, then we say that limit of the sets exist. So this would happen if, as we have discussed in the proposition above, if the original sequence an is increasing or decreasing, this will happen. That was a part of the proposition above. So in general, if it so happens that limit inferior and limit superior match, then we shall write that limit of ans exist, and it will be equal that limit inferior or limit superior in this equality case. Okay, so the limit will be equal to the limit inferior and limit superior, that equal the common value here. And another important observation, take a measurable space. So that means script f is a sigma field on this non-empty set omega. And if it so happens you have a sequence of sets in the sigma field, then if you look at this construction of limit superior and limit inferior, they involve certain countable unions and countable intersections. you will immediately claim that since a sigma field script f is closed under countable unions and countable intersections, the limit superiors and limit inferiors must belong to script f. So again, this is immediately following from the definition of a sigma field. Further, if you have additional information, right, like an's increase or an's decrease, then of course this limit, this common value of the limit inferior or limit superior, so that's the common value. So let's call that a again. So that will also belongs to the sigma field. So we will again use this later on, but this is an important observation that take any sequence of sets coming from a sigma field, then their limit inferior or limit superior are certain sets involving countable unions and countable intersections. That's how they are defined, and they will belongs to the sigma field. So in this regard, there is this interesting connection with the usual notions of limit superior and limit inferior that we have seen for sequences of real numbers. So that connects involving certain indicator functions of sets. So what are these? So take any subset A of omega, a non-empty set. Then you say that the indicator function of the set A is this function. I will write 1 underscore capital A. It has a domain omega and it takes value 0 or 1. So if you take a point in omega, small x in omega, then the indicator function will give you 0 if the point is not in the set A. Otherwise it will put 1. If the point is in A, then you will put 1. Okay, so that's the indicator function. So it has two values. You just check if arbitrary element x belongs to the set or not. If it belongs there, you put 1. If it does not belong, put 0. Okay, that's the indicator function of the set. Now look at a sequence of subsets. What you can now try to show that for all x in omega, if you look at limit inferior of this indicator an evaluated at small x, so the left hand side, if you fix your small x, then indicator an of x, this is a sequence of zeros and ones. So this is a sequence of real numbers. So I am looking at limit inferior of that, and on the right hand side I am looking at indicator of the limit inferior of the sets. Now this is a set, limit inferior of ans, this is one set that we have discussed. So I am looking at indicator of that and I am evaluating at the point small x. So on the left hand side I have a sequence of zeros and ones. I am looking at limit inferior of that. On the right hand side I also have a 0 1 valued sequence, but the limit inferior is taken in terms of the sets. A similar statement also holds for limit superior. So again, on the left hand side I have a sequence of zeros and ones. So I am just putting this, I am fixing that small x. I am just checking whether the small x belongs to the ans or not. So that's how I am getting this sequence of zeros and ones, and I am computing the limit superior. And on the right hand side I am computing the indicator of the limit superior that we have defined. So on the right hand side, limit superior is in terms of the sets, and then I am evaluating that function at the point small x. Okay, so these will connect the notions of limit inferior, usual sense of real numbers, sequence of real numbers, with notions of limit superior and limit inferior of sets. So we stop here.